Here we are in section 1.2. Again, this should be another review section out of chapter 1 that we will go very quickly through. Again, these are all the things that you should be coming into Calc 1 knowing. This is just a reminder of those things, and actually there's a huge amount of stuff here in section 1 too on graphing and functions and transformations, defining what piecewise functions are, etc., etc. So we're going to go forth and figure this out. So this section will be a huge review of multiple types of functions that we will be working with during this semester. It is crucial for that you are familiar with them, their properties and their transformations. So the first group that we're going to look at are polynomials. And polynomials basically are those, let me get my pen here, those of the form p of x is equal to, where I have a sub n x to the n plus a sub n minus 1 times x to the n minus 1 plus, and it keeps going until you end up getting like a sub 1x plus what we say a naught, which is the constant there, and where each one of those numbers in front are what we refer to as the coefficients, a naught, a1, all the way up to a sub n. Now, they are real numbers with a sub n not equaling 0 and the non-negative integer n. So this power here is always a positive number. That is the degree of the polynomial. Now, the domain of any polynomial is all real numbers. That means that any number can go in there and can be multiplied and added and subtracted to whatever it has within there. Now, an nth degree polynomial can have as many as n real zeros or roots. Not only is it the degree, but that tells you how many answers make that polynomial equal to 0. And those zeros and roots are where those values that are coming up here, where they are real zeros or roots, which are values at x of x at which p of x is equal to 0, and the zeros are the points at which the graph intersects the x-axis. I was going to say that earlier, but I'm giving it away before I get there. So if I have a parabola and it does something like this, then here are the roots and the zeros. That's where they cross the x-axis. So some examples of polynomials could be p of x equals x cubed plus 3x minus 1. I could have something like p of x equals x to the 7th. I could also have something like p of x equals 3x squared minus 4x minus 5 or something like that. Those are all polynomial functions. All right, let's move on to rational functions. We alluded to some of this in section 1 on rational functions when we were talking about the domains. Ratios of the form f of x equals p of x over q of x, where p and q are polynomials. So it's basically two of what we just talked about and divided together. Because division by 0 is prohibited, the domain is the set of all real numbers except where the denominator is 0. And we saw that in the last section as well. So we look at whatever makes the bottom 0 and exclude that from our domain. Algebraic functions makes use of algebraic operations of add, subtract, multiply, divide, and also roots. And the domain of that radical function, if you have added and subtracted together, the root is the main part of there. We again alluded to this also in the last section, where the radicand has to be greater than or equal to 0. And that radicand is whatever's underneath that square root. So you want to jot it down over here or something like that to remind you. The radicand is what's underneath. So I could have something like f of x is equal to the square root of x squared plus 10. That would be an algebraic function. I could also have one in fractional exponent form where I have like x to the 1/4 times x cubed plus 2 or something like that. So that would be a algebraic function as well. Now, breaking into some exponential functions, these are the ones that kind of get a little bit different whenever we're working with not only exponentials, but natural exponentials and also logarithms and natural logs. Those two things are inverses of each other. They are the things that undo themselves, just like add undoes subtraction, multiply undoes division, square rooting undoes squaring, etc., etc. So these functions have the form f of x is equal to b to the x, where the value of b is not equal to 1, so it's some other number besides that, could be positive, is where b not equal to 1 is a positive real number. The domain of an exponential function is all real numbers, so you can plug anything into that power and take that base to that power. Now, the natural exponential is of the form where I have f of x is equal to e to the x. So here's kind of a basic graph of an exponential. That's what that looks like. Remember that e is approximately 2.718. It is just a constant. Hello. I should finish my sentence first. Where e is approximately 2.71828. And again, it is just a constant, just like pi. And so we will kind of allude to where that natural exponential comes from when we're starting to talk about some derivatives. Now, the inverse of exponentials are what we call logarithms. Or, in some case, if we have the function for that, log base b of x, where b is going to be greater than 0 and b is not equal to 1. And so this is an exponential here. The graph of a log, kind of a basic graph, is if they're inverses of each other, then instead of the point being at 0, 1, now we're at the point 1, 0, and it's actually going to be symmetric over the line y equals x. So that's kind of a basic log graph there. And so if you notice that the domain of a logarithmic function is everything from 0 to infinity. That would be what the range is of the exponential function. Again, they are inverses, so they would be backwards of each other. Now, the inverse of natural exponential is called a natural log, or of natural exponentials are natural logs, or the notation for that function is f of x is equal to ln of x. Now, some people get that confused, this to be an I. Remember, that's a lowercase l. I guess sometimes I probably will allude to doing like a cursive L, but if you're ever entering anything in, like to my lab math or anything like that, make sure you use an L and not an I, because it will mark you incorrect. Now, notice here it does not have a base like what we have up here, so that means that the base of this one is understood to be E. Okay? Now, if I have, let me put that in here. If I have f of x equals log of x, then the base here on this one, where it is not given, is assumed to be 10. Okay, so if you need to go back and brush up on some logarithms and exponentials, we won't do a whole lot with them, but we will end up working with them. Here are some examples of exponential functions and log functions. We have y equals 3 to the x. I could also have y equals e to the 4x minus 2 or something like that. Then, in a sense, for a logarithm function, we would have y is equal to log base 2 of, say, x plus 3. And I could do a natural log where I have y is equal to the natural log of 3x plus 2 or something like that. So, again, a little bit of a delay. Apologize for that. But we have y is equal to natural log of 3x plus 2 would be an example of a natural log equation. And our last one that we're going to talk about before we kind of sum them all up is trigonometric. And so, trigonometric functions are fundamental to mathematics and, kind of cut that off there. Areas of application, the 6 basic trig functions are the sine of x, the cosine of x, tangent of x, the inverse of sine is cosecant of x, the inverse of cosine is secant of x, the inverse of tangent is cotangent of x, and don't forget about inverse trigonometric functions. That will actually give us an angle versus a value within that trig function. So remember this is the way I remember inverses. Sine and cosine, you have to have a C and an S each time. A C and an S each time. So cosine and cosecant can't go together. They have to be different. Sine and secant can't go together. It's sine and cosecant, cosine, secant. Okay? So we'll do a lot of that with working with those and doing derivatives and integrating and such later on in calc. Here is an example of a trigonometric function where I have something like y is equal to the sine of x minus pi over 2 plus 3. I could also do something like y equals -2 tan of x plus pi over 4 or something like that. Okay? All right, now the last type of function that we talk about kind of molds together trigonometric, exponential, and logarithmics. Those are what we refer to as transcendental functions. And so I will kind of give you something to look at if you wanted to. There's a diagram, a Venn diagram on page 14 that's very, very helpful when looking at some of those things, okay, as to how they all relate to each other. All right, so let's move into talking about linear functions. So the rest of this page is on that and part of the next page, and then we'll get into some other different types of functions. And then the big part for this section is the transformations. So we will see how that works in that. Okay, so linear functions. It is crucial that you know how to write the equation of a line. And know how to work with slopes and stuff, because a lot of what we do in calculus stems from knowing these basics. So if I have just kind of some hit and miss basic facts here in this chart about lines. Slope between 2 points, say if I am given the point x1 comma y1 and the point x2 comma y2, I'm going to end up finding the slope between those 2 points of y minus y over x minus x. Remember when you're finding slope that once you start with one point, go back to that other point and do the difference of the x's. If not, you're going to get a sign change. So this is kind of what we referred to yesterday, or not yesterday, on the previous section about the slope of the secant line between point P and Q. We found that in terms of the difference quotient. So we'll be working a lot with slope of lines, okay? Slope from a standard form. So if I'm given ax plus by equals c. Now some standard forms are ax plus by plus c equals 0. We're going to say the standard form is this. If I'm finding the slope from that equation, slope is found by taking the opposite of a over b. So the opposite of the coefficient with the x all over the coefficient of the y. So kind of a shortcut. You don't have to solve for y equals mx plus b. You can, if you want to, and pull out the coefficient of the x, but you don't have to. All right, here's a biggie. Point slope form. Notice I have my stars on here, so if you need to do an extra star, please do so. Given any slope and a point, you can always write the equation of a line. So you need to make sure that you can start with point slope, because no matter if I want to end in slope intercept form or into standard form, it's very, very nice to be able to start with point slope and go to whatever form that you need. Point slope is defined by y minus y1 equals m times x minus x1. And that is very, very, very important. Slope intercept form is where you are given an m and a b. Now remember that m is your slope, b is your y-intercept. So if I write it as an ordered pair, it will be the point 0b. For any y-intercept, our x is equal to 0 always. So the slope-intercept form is y equals mx plus b. That's one that's kind of ingrained in your head in Algebra 1 and Algebra 2. Then we have standard form. We talked about that up there. For our standard form, takes of the form ax plus by equals c, where a, b, and c are integers. Integers are positive and negative whole numbers. There are no fractions or decimals as your coefficients, okay? And I'm going to add one thing. Normally a is positive, so we want to make sure that a is positive, no fractions within that. I mentioned what a y-intercept looked like, where x was equal to 0. So if I'm trying to find the intercepts, then we're going to let x equal 0. If I want to find the x-intercepts, which is also what we referred to just previously about the roots and zeros, then we're going to let y equal to 0. So sometimes when you're graphing a line, it's a lot easier to graph the intercepts and use this method than it is to put it into y equals mx plus b form and graph using slope-intercept form. All right, moving on to horizontal lines. Horizontal lines we'll talk about a lot in calculus when we have a horizontal tangent and such. They have an equation of the form y equal to some number, or f of x is equal to some number. So it's just one variable equation, and it does have a slope of 0. Vertical lines have an equation of the form x equal to some number, and the slope of a vertical line is undefined. Now, maybe I go back up here when I talked about slope of a line. So if I have a line that goes this way, that is a positive slope. If I have a line that goes this way, it's a negative slope. Okay, a horizontal line is one that is constant straight across. So I always kind of refer to, if you're going left to right, going up, you're walking up a hill, it's going positive. If you're walking left to right, down the hill, that has a negative slope. If you have a horizontal line, it is one that is constant, no slope, no slant. That's why we have 0. We can walk along this constant line, but if I have a vertical line, no way of walking along that vertical line, I would fall off due to gravity. Therefore, we are undefined on that slope. A way to remember that. All right, we will be working with some stuff, parallel, perpendicular lines. So as a reminder for those, if we have parallel lines, they have the same slopes or equal slopes. And for perpendicular lines, they are not equal. They have to be two different signs. And what we refer to them as are opposite reciprocals. So in order to get an opposite, you have to do two things. One thing is that you have to change the sign to get the opposite. And to find the reciprocal, you have to flip your fraction. So if it is equal to, say I have a slope here of, say, 2/3 or something like that. The parallel slope is the same. It's 2/3. For the perpendicular slope, I have to change this from a positive to a negative and flip it. Therefore, it would be -3/2. So hopefully you remember that. So let's see what we can do here. Find the equation of a line that is parallel to the lines it passes through the points 3, -1, and -3, 3. And goes through 5, -6. Okay, so we are going to first have to, we have a point that we want to go through, but we don't have a slope, but we're given these 2 points. So we're going to steal the slope from that. The slope, using my slope formula, go y minus y. 3 minus a -1 becomes a +1. And then go -3 minus 3. Therefore, we have a 4 over -6, which is -2/3. Therefore, the parallel slope that I'm looking for, remember they're parallel lines, they have the same slope, same slant, that would also be -2/3. So I'm going to take -2/3 along with the 0.5, -6. Start with your point slope form. Y minus y1 equals m times x minus x1. Plug those numbers in and solve it in terms of x and y. So y1 is this guy over here, so I get y minus a -6. So double negative again becomes a +6. The slope we found was -2/3. And we have x minus the x value, which is 5. All right, now let's just say we want this equation in y equals mx plus b. We want to solve for y, which is a lot of the times what we do. It's more practical than for solving for standard form. So I'm going to go ahead and distribute this here. So this gives me y plus 6 equals negative 2/3 x. A negative times a negative becomes a nice little positive. And 2/3 times 5, unfortunately nothing to cross cancel, just gives me a 10/3. And my final answer is going to come by subtracting 6 from both sides. Therefore, I get y equals negative 2/3 x, and this out of 3 would become an 18 out of 3. So 10/3 minus 18/3 is a negative 8/3 would be my intercept within that line. So y equals negative 2/3 minus 2/3 x, minus 8/3 would be our answer. All right, now let's find the equation of the line that is perpendicular to the line 2x minus 4y equals 8. And this time we are going to pass through the point negative 1, 3, let's say. Okay, so again, I need a point and a slope in order to write the equation of the line. Here's my point. I'm going to steal my slope from right here. Now this is an equation. So we can go back up at the very top of that chart and it says given standard form, what is the slope of a line? Opposite of a over b. So the opposite of the x coefficient over the y. So I would get m to equal negative 2 over negative 4, which actually gives me a slope of 1/2. Now that's the slope of the line, but I want to be perpendicular to that. Therefore, the perpendicular slope of this one is going to be, what do I have to do to get perpendicular? I have to change the sign and I have to flip it. So you could write it as negative 2 over 1, but I'm just going to write it as negative 2. Therefore, I'm going to y minus the y value from my point slope form is equal to my slope, which is negative 2 times x minus a negative 1. So double negative again becomes a plus 1. And now all we have to do is distribute. So I get y minus 3. Distribute gives me negative 2x minus 2. And when I add 3 over to the other side, I get y is equal to negative 2x. When I plus 3 and plus 3, that gives me a plus 1. So that would be my final answer for that equation. Okay? All right, very good. Now, here's just an exercise in graphing those lines. Making sure that we are able to graph in a point, well, not a point slope, but in y equals mx plus b form. And so, again, b is the number that's added at the end. We're going to use our slope to find the next point. So for part A, I was going to go up to 1 as my intercept. Now notice this is a negative 2/3. So I could bring that up as a negative 2 over 3, or I could do 2 over a negative 3. Doesn't matter as long as you only give it to 1 and not both. So for the first one, slope is rise over run. So we're going to go down 2 and over 3. 1, 2, 3. So I could get this point. But if I look at it as this way, that means I'm going to go up 2 and to the left 3, which would give me this point right here. Whichever way that you do it, try at least have 3 points. I like to use 3. I know you only need 2, but try to do 3 points just to make sure you're on the right track. All right, what about x equaling 4? Well, I have x equal to a number. So if we go back up here, x equal to a number is a vertical line when x equals 4. I like to remember it as I'm going through the x-axis. When I have x equal to a number, going through the x-axis. Y equal to just a number goes through the y-axis. So x equaling 4 is going to be this line right here. So I'm going to mark that one as A, mark this one as B, so you know the difference between the two. And we have f of x equals 2x. Now remember, f of x is the same as y. So I could have y equals 2x is another way to write this. Now, notice there's no plus or minus here at the end. I could always add a 0 to not make any difference. So that means that this line is going to go through the origin. And I'm going to write that slope as 2 over 1. So remember, rise over run. I'm going to go up 2 and over 1, up 2 and over 1. There's my 3 points. That's good. If you just wanted to go down 2 and over 1 just to get another point on there, you are most capable of doing that as well. So that guy right there is line C. And the last line that we have here is f of x equals -2. So I'm going to say y equals -2. And so again, that only has one variable, so that is a special line. It's either going to be a horizontal or vertical, but it has to go through the y-axis at y equaling -2, which is down here. Therefore, that horizontal line looks something like that, and that is line D. So, making sure that you can graph a line, making sure you can do the slopes, make sure you can write the equation is a big one for your lines. Okay? All right, so let's look at a kind of a real-world application of that on the next page. And it says that after studying sales for several months, the owner of a pizza chain knows that the number of two-topping pizzas sold in a week, called the demand, decreases as the price increases. Specifically, her data indicates that at a price of $14 per pizza, an average of 400 pizzas are sold per week, while at a price of $17 per pizza, an average of 250 pizzas are sold per week. Assume the demand D is a linear function of a price P. So that means that D is going to be my input, okay? So, the demand is a linear function of the price P. Sorry, the P is, once I have the price, then the demand is determined by the price. Sorry, so we're going to have P be like our X and D be like our Y. So if I try to do that kind of in a point form, price, comma, the demand. So P, comma, D is what I want. And given the information, you can write points for that. So if I have a price of $14, the demand is 400. If I have a price of $17, the demand is 250. And so now, given these 2 points, we could actually go forth and find an equation, which is what they asked for in part A. Find the demand function as a function of price. So this is going to be like our X, and this is going to be like our Y. So I'm going to find the slope real quick of this and go 250 minus 400 all over 17 minus 14. This is negative 150 over 3. Therefore, my slope is negative 50. To find that demand function, we want D equal to, okay? So I'm going to go ahead and use the D and the P. So we're going to go D minus. Now choose some point. Doesn't matter which point you're going to use. I'm just going to choose this first one. D minus 400 equals my slope, which is negative 50, times P minus the 14, which is our price. Now, you could have used this and it would all work out in the wash, but you're going to end up with the same thing. Doesn't matter which one you use first. So I'm going to distribute the negative 50. This would then give me a positive 700. And then when I add 400 to that, my demand function is negative 50p plus 1100. And that will be our function. It's a linear function, okay? In terms of P, that'll kick out a D. Part B, though, then tells us or asks us, according to this model, how many pizzas on average are sold per week at a price of $20. So I need to know the demand, given that the price is equal to 20. So if I already have a function for that, I can take that 20 and put it right in for P and figure out what D is. Therefore, D is equal to negative 50 times 20. Add to that 1100. Negative 50 times 20 is a negative 1000. Plus 1100 is equal to 100. And that is the demand if we were to sell those pizzas for 20 bucks. Okay? All right, very good. So that's kind of the review on just the lines and the linear functions, but we're now going to move and evolve into piecewise functions. And if I were to kind of break that apart just into its first term, piece, we are going to piece a bunch of functions together to make a new function, okay? So functions that have different definitions, different equations for different parts of their domain are what we call piecewise functions. And what I used to do when I taught high school with Algebra 2 and Algebra 2 trig, and even in math analysis, we would do an activity where we had graphs, and I actually made them cut out parts of the graph and piece them back together on a separate graph so they could see that idea of basically cutting up the functions and putting them all together on one according to their domain. So you have multiple functions on one graph, but they are restricted by their domain. So let's just try this. Here I have a line y equals x plus 0. So mx plus b. I have an intercept of 0. The slope is sitting out here as a 1. It would be 1 over 1. So I would end up having this line, okay? Now, that entire line looks like this, but I have a restriction on that. I have the restriction that I can only be on that line of y equal to x if I am less than 2 on the x. Well, here's x equaling 2. Where am I at? Less than would be all of this. So now notice I don't have an equals. So I'm going to grab this little eraser here. I'm going to erase this part up to there. And when I don't have an equals, that means I can't have a solid dot there. I've got to end up having an open circle at x equaling 2. So that is the line y equals x, but I'm restricting its domain from x equaling 2 and down. So we only draw that portion of it. Now look at what happens when I'm equal to 2. Now that's only one spot. The kick out of that function is 3. So this is a y value, that's an x value. In disguise, I could write that as a point of 2, 3. And when I do that, the solid version, because that's where it's equal to when x equals 2, has to be a solid dot there, not an open dot. That's only when it's not equal to. And then I have my last piece of my function for all values that are greater than 2. So everything over here. Now there's one of two ways that you could do this. You could go up here and kind of identify where that y-intercept is at 5. Using the slope, I could go down 1 and over 2, down 1 and over 2, down 1 and over 2. You can do that if you want to do that. Or what I also like to do sometimes is, what if it's equal to 2? Where would it be? Well, negative 1/2 times 2 plus 5. Negative 1/2, that's a negative 1 plus 5 is 4. So I kind of went through that. If I intercept here, down 1 and over 2 gives me this. Now I'm going to open circle there. So you can find where that's at, and then you could also plug in x equaling 3. Put 3 in here. Where are you going to be? You can put 4 in there. Where are you going to be? But you could also here step in and use the slope and go down 1 and over 2. Down 1 and over 2 would also give you that, and then we would end up finishing our graph by connecting those. So you have domain here of all real numbers. It's just pieced into different things in which you have a portion of y equals x, that point when x equals 2, and this portion of that line when it's greater than 2. All right, let's try this next one. Here we have two domains, everywhere where x is not equal to 2 and everywhere where x equals 2, but that's only 1 point. So I'm going to go ahead and get that out of the way. Go over 2 and up 1. When x equals 2, y value is 1. Now, here, if I asked you what the domain is, we could not allow x to equal 2 because that would make the denominator 0. So how am I going to plug in values? Because I'm just going to get a 0 over 0 in some cases. So I'm going to factor this and see if I can simplify this rational function even more. So this x squared minus 5x minus 6 does factor as an x minus 2 and an x minus 3. So I'm going to be able to cancel and cancel. So basically the graph that this is taking on is a linear function, but I have to skip over when x equals 2. So let's find out where that line is. That line's going to go through the intercept of negative 3 by a slope of 1. I'm going to go up 1 over 1, but get ready. I'm getting ready to get to x equaling 2. And I have to go back and erase some too because I forget to leave a hole. Up 1 over 1, that's where my hole has to be. And I can go up 1 over 1, keep doing that pattern. It's going to be defined everywhere except for where this hole is. And so that would be the graph of a piecewise function where we have two different domains, and so two different functions on that. There being one, and the line without that point is the other. Okay? So you'll be able to kind of identify some of those, graph some of those as well on yours, so make sure you practice that. Okay, absolute value. Absolute value is a function that we we'll define, and I'll do kind of the parent graph here for you, but it is actually, why is it here with piecewise? It's because it's actually a piecewise function. So if you start plugging in values, 0, absolute value is 0, absolute value of 1 is 1, absolute value negative 1 is 1. If you start plugging in values, what happens on an absolute value function is that that guy looks like a V. So how is this a piecewise function? Well, what do you have here? If you continue this line all the way down, I've just cut it off basically right here at x equaling 0 and only doing that portion of that line. This line we just graphed in our first piecewise example right up here, and that is the line y equals x. If I were to go back up a little bit, y equals x is right there. And so this is y equals x, but it's only for when x is greater than 0. So that means that if I try to find the value of the absolute value for any number, if x is, and we can kind of throw the equals where we want, I'm going to put it on this one, then any value that is greater than 0 has an absolute value that is the same as that number. So it would just be defined as x. Basically, the absolute values go away. But if I end up looking at this, if I say, okay, x, put in an absolute value, I get a positive 1. Throw in negative 2, I get a positive 2. So that basically kicks out the opposite of what we're plugging in. So as defined for the absolute value function, it is also equal to negative x, and that is only when x is less than 0. So we do have a piecewise function here. It is one that you probably want to remember, because we do kind of break down some absolute values often, depending on which side that we're coming in around that vertex. Okay? All right. These two are some good function work with piecewise. I like to throw these in here because there is some similarity things that are going to happen when we talk about slope. So this slope function is kind of important to see as a piecewise function. And then the area function is just some good stuff for us to kind of think about, some critical thinking questions, and end with a piecewise function. So let S be the slope function of f. S is the slope of the curve at any point. So if you look at this graph down here, here I have a line that has a certain slope. Now if we look right here, that line is equal to, you do 2x or 2t in this case, and that right there is actually claiming to me what the slope is for values from 0 till I stop on that line at x or t equaling 3. So if I'm looking at a slope function, we'll call it s of t, since we're in a t value, from 0 to 3, and I'm going to symbolize that for if 0 is less than or equal to x, which is less than or equal to 3, the slope from this line to here is always going to be 2. Notice here I go up 2 over 1, up 2 over 1, up 2 over 1. So the slope is 2 if we're between 0 and 3. Now, at 3 and beyond, we're going to say that this keeps going on. So if, whoops, I used the wrong letter. Make that a t. So if t now is greater than 3, notice I put the equals here, so I'm not going to put the equals here, because if I do that, then it's not a function. From anything greater than 3, we are on this constant line of y equaling 6. Okay, well, what's the slope of a constant? Well, that means I don't go anywhere, but I go over 1. So the rise is 0 over the run of 1. Therefore, the slope of that constant line is 0. So this would constitute the slope function for the graph that we see right here. Okay? Not too hard. You just have to kind of realize what is slope and what is not. Okay, so the last part of this page is talking about an area function. So with the area function, we're going to find the area of this shape that is bounded in the first quadrant. Let A be an area of the region bounded by the graph of f and the t-axis from t equaling 0 to t equaling some x along here. Okay? So we want to know what's the area of A of 4. So our x value, or our t value that we ended, is at 4. So notice, there's a couple ways we can do this. This is actually a trapezoid, so we're looking at this area right here. That's actually a trapezoid that we could actually find the area of, Or it is also the area of a triangle and a rectangle. So not very many people remember the area of a trapezoid. So if I can take the area of this triangle, add it to the area of this rectangle, then I have my total area. So we're going to say A of 4. Well, the area of a triangle is 1/2 base times height. So I'm going to go 1/2. Our base here is a unit of 3, and our height is 6. So 1/2 of 3 times 6. Add to that the area of a rectangle. Again, the area of a rectangle is length times width. So we have a width of 1 and a length of 6. So we want to go 6 times 1. So the A of 4 is defined, well, half of 18 is going to be a 9 plus a 6. Therefore, my answer for A of 4 is going to be 15 as defined by this function. But the other thing is now we have to find the area function for F. Now, it's different. It is different. I'm going to get rid of this stuff on here so I can kind of draw. Now, if I were just on the triangle, I would be able to find the area of that triangle, okay? No matter what my x value is here along T, I can stop and find the area. That's going to be the area of the triangle is 1/2. Now, we don't know what x we're stopping with, so we're going to do this in a variable form. So maybe I'm going to let this be x, okay? The corresponding height right there, remember, is f of x, okay? And it is along this line of 2t, okay? Or if I throw x in there, it would be 2x, okay? So the area of a triangle is 1/2 of its base. Well, the base up to x is going to be x times the height. Well, that's the f of x. What was f of x? If I throw that in there, what is it? That length is 2x. And so I can simplify this expression and say, okay, half of 2 gives me 1, therefore x times x is x squared. So if I am anywhere from 0 to 3, the area of that function, the a of x, is going to be x squared. So B, we're going to do a of x is equal to, if we are from 0 to 3, then our area is going to be x squared. Now, if our x is beyond that, what would we do? So sometimes you have to break these things up, okay? And we'll see that later on too when we're dealing with integration and maybe some derivatives and such. You got to kind of break these things up. All right, so what if my x value is over here, where I end up having a rectangle and a triangle, okay? So this area up to this point, just like what we did here, was what? We accounted from 0 to 3. That gave me an area of 9. So I'm going to have, let's do area of the triangle plus the rectangle. That is going to be 1/2 of 3 times 6. But the area of my rectangle differs than if I'm over here in this area. Okay, so if x is here, it's going to be different than if x is here. If x is over here, it would be different. But how do I determine what this distance is? Well, this distance has to be 6 every time, right? And no matter where you're at, that length is going to be 6. This part right here is the trickiest. Because I don't need all the way from 0 to x, I only need from 3 to x. So when I'm finding a length here, the distance formula says you have to take x minus 3. So from 5 to 3 is 2 because you take 5 minus 3. From 7 to 3, or 3 to 7, it's 7 minus 3, so that's a distance of 4. So this distance from 3 to x has to be x minus 3. So I'm going to add to that the width times the height, which is 6. So notice here we do have an expression that we can actually work out a little bit. So this is going to be, we already found that to be 9. Plus, when I distribute this 6 through, I'm going to get a 6x minus 18. Therefore, we end up having to combine here, gives us a 6x minus 9. Therefore, the area of this is going to be 6x minus 9 if our t-value is greater than 3. Again, you can't have an equal in both spots. You only have to have an equal along where they are common in one spot or the other. So this would be my area function. It's a good little critical thinking problem of what happens when you have to piece things together. Okay? Do some specific examples if you have to help yourself out in that case as well. All right, very good. So let's move forth into transformations. Actually, I think I'm going to stop here on this video so it doesn't get too long for me to be able to upload it. And then I will come back with a part 2, and we will do the transformations, which hopefully will be going very, very quickly for things that you should recognize. So come back for part 2.